Okay, so yeah, welcome again. So I guess today Rajas will continue his discussion on Kähler geometry. So he will talk on overview of some concepts related to holomorphic line bundles. So yeah, over to you, Rajas.
Okay, thank you, Sachidananda. So today in this talk, I will continue about the prerequisites from Kähler geometry that are needed for my series of talks. So today I will be talking about these holomorphic vector bundles and holomorphic line bundles. So just like we have vector fiber bundles and vector bundles over smooth manifolds. So similarly, we will be having those things on complex manifolds as well. But now here we require them to be holomorphic. So we will see what these notions are. Okay, fine. So let me just start. Okay, so fine. So we will first see what is a holomorphic fiber bundle. So we know that in the smooth category, meaning in the case of smooth manifolds, we have fiber bundles over smooth manifolds which have got a local trivialization such that the transition maps are going to be smooth maps. But over here in the co- category of complex manifolds, we are going to be having a holomorphic fiber bundles. So this pi from E to B, where E and B, both of them are some complex manifolds. Pi from E to B is a surjective holomorphic function. So then every element say, P belonging to B has got a fiber over it, which is pi inverse of B. And then all of these fibers are going to be biholomorphic to the typical fiber space capital F. So we will see how this happens. So we first have a open covering of the base space. So this capital B is called as the base space, capital E is called as the total space, and pi is called as the bundle projection. And this capital F is called as the typical fiber of the bundle. And then we have this U alpha, which is an open covering of the base space. So the and then for every open set U alpha coming from this open covering, we take pi inverse of U alpha. So this pi inverse of U alpha should be biholomorphic to U alpha cross F. Uh, so this is what it means to say that the bundle is locally trivial. So like this B cross F over B. So this B cross with F over B. So this is what we call as the trivial fiber bundle over B, where uh, it is just the Cartesian product of B with F. But these locally trivial fiber bundles are ones where in every uh, local open set we have got this biholomorphism. So locally this total space capital E looks like B cross F. So for all of these pi inverse of U alpha, we have got a biholomorphism with U alpha cross F, and we call these local trivializations as phi alpha. And then these local trivializations satisfy one more property, namely that the local trivialization it looks like the standard projection standard projection map onto the base space. So like this pi subscript capital B is the standard projection map. So if you compose this standard projection map with phi alpha, you get the bundle projection pi. So this additional property has to be satisfied. Then these phi alpha are called as local trivializations of the bundle. And one more thing is regarding the transition map. So if we take any alpha and beta such that U alpha intersection U beta is non-empty, then this phi beta composed phi alpha inverse, this is our transition map. So this transition map here is required to be holomorphic. So note that in the smooth category, the local trivializations as well as the transition maps were required to be just smooth. But here in the category of complex manifolds, we require these maps to be holomorphic. So this is what we mean by a local holomorphic trivialization. Okay. So these transition maps are going to be holomorphic, and then at every point belonging to the intersection U alpha intersection U beta, it will induce a biholomorphism of this typical fiber capital F. So, and this holomorphism phi sub alpha beta is given in this way. So, and then these phi sub alpha beta, they satisfy one more additional compatibility condition, which is sometimes called as the co-cycle condition. Namely, this phi gamma beta composed phi beta alpha is equal to phi gamma alpha for all indices alpha beta gamma, such that this intersection is non-empty. So this entire data is called as a holomorphic fiber bundle. So you can see that the holomorphic fiber bundle is defined in exactly the same way as a smooth fiber bundle. Just like we are now in the holomorphic category, so the all the maps are required to be holomorphic instead of smooth. So okay, so this is a holomorphic fiber bundle, and then so what we are interested actually in are holomorphic vector bundles. So a holomorphic vector bundle is simply a holomorphic fiber bundle such that the typical fiber capital F is nothing but the this complex vector space CR, which is also an R-dimensional complex manifold. And then additionally, the induced functions that we have, these phi alpha betas, sorry, phi beta alpha. So these phi beta alphas, these induced functions which we have here, they were just biholomorphisms, but now in the uh, case of holomorphic vector bundles, we require them to be C-linear maps. So they are C-linear isomorphisms, or C-linear automorphisms of the complex vector space CR.
Yeah,
So that's
Rajesh,
why
so
the
there is a question. So
yes,
maybe
sure, yeah, Prahlad,
so
yeah, sure, go ahead.
Raja, I think these, as what you said, just that, or also you wrote down there, the typical fiber is complex RPCR. Is
Yes,
ideally it is not, right? Because it is isomorphic to CR. So typical
like
fiber is generally isomorphic to CR. Once you trivialize it, then it becomes CR with respect to some basis, right? So I mean, when you in my mind, like when you say CR, a typical fiber is, then CR is usual shear with the usual standard ordered basis.
correct.
But in that sense, I'm saying, so if you move fiber to fiber, then your vector space, of course, that is a r-dimensional complex vector space, but it need not be canonically CR always, right? Otherwise, your bundle would be trivial bundle.
So the thing is that this typical fiber capital F that I'm talking about, that is not equal to pi inverse of some point. Like it is not the fiber over a point. It is just some fixed complex manifold, or in this case, a complex vector space. So like that is different from pi inverse of B, like pi inverse of some
Oh,
point P
I see,
belonging
I
to
see,
B.
I see, I see. As you said, VEF or complex manifold in that sense. Okay, no problem. Yeah.
Yes, yeah.
Okay, thank
Yeah,
you.
so like
Sorry.
you are right that then each fiber pi inverse of small p, where small p is any element of the base space capital B. Yeah, that each fiber pi inverse of small p will be biholomorphic to the typical fiber, or in the case of holomorphic vector bundles, it will be um, biholomorphic to CR, where the biholomorphisms are precisely given by the local trivializations itself. So that's the thing. Okay. Yeah. So like in the case of holomorphic vector bundles, these induced functions phi beta alpha, they are C-linear isomorphisms, and that's why then this beta alpha, they will then become R cross R complex matrices, invertible complex matrices. So then this compatibility condition or co-cycle condition, that will become like that will be then given in terms of matrix multiplication. So these will be then elements of the complex general linear group GLNC. Okay, so that's why like so this is a holomorphic vector bundle, and then this non-negative integer r that we have, this is called as the rank of the holomorphic vector bundle, and then rank one holomorphic vector bundles are just called as holomorphic line bundles. So okay, so these are what are holomorphic fiber bundles, and then holomorphic vector bundles, and holomorphic line bundles. Okay, so before like going to some examples, so there is also one more notion called as a complex vector bundle. So note that a complex vector bundle is different from a holomorphic vector bundle. So the difference is that in a complex vector bundle, we have the same data as that of a holomorphic vector bundle, meaning we have this base space, total space, and the bundle projection as well. And this CR, we have this complex vector space CR. So we have all of these things. The only conditions which are dropped are that the local trivializations as well as the transition maps, they are just smooth maps instead of being holomorphics, but being holomorphic maps. But these induced functions phi beta alpha, they are still required to be C-linear isomorphisms. So it's like it is just a smooth vector bundle, but the vector spaces, like all the fibers are isomorphic to CR, and they are complex vector spaces. So that's why we require these induced functions phi beta alpha to be C-linear isomorphism. So this is what is called as a complex vector bundle, and it is in this way different from a holomorphic vector bundle. A holomorphic vector bundle is a more stronger notion. Okay, so now I will just give some canonical examples of these holomorphic vector bundles and complex vector bundles which are associated to any complex manifold. So like associated to any smooth manifold capital M, we have the tangent bundle of the manifold and also the cotangent bundle of the manifold. So to a complex manifold, we will be having we take the holomorphic part. So it is the holomorphic tangent bundle and the holomorphic cotangent bundle. So these are two important examples of holomorphic vector bundles. And for complex vector bundle, we can simply take the complexified tangent bundle and the complexified cotangent bundle. So now in this thing, what is the difference between the complexified tangent bundle and the holomorphic tangent bundle? So I will have to go to the whiteboard to explain. Okay, okay, so in the last talk, we had just discussed about what is the complexification of a real vector space. So we simply take that real vector space, and then the vector space C is going to be a two-dimensional real vector space. We simply take the tensor product of these two over R. So this TPMC is what is known as the complexified tangent space. So it is simply the complexification of the real tangent space. So we simply take the tensor product of the real tangent space with the two-dimensional real vector space C. We take this tensor product over R, and then we had seen that this TPM tensored with C, this can be turned into a complex vector space. So this is what is called as the complexification of TPM. So this is the complexified tangent space, and then the uh, bundle corresponding to these complexified tangent spaces, which will be the disjoint union of these complexified tangent spaces, that is called as the complexified tangent bundle. And then this complexified tangent space has got the square root of -1 eigenspace and the minus square root -1 eigenspace, which are the two eigenspaces corresponding to that almost complex structure J. So we had this almost complex structure J on the real tangent space, which turned it into a complex vector space, and this satisfied the property that J square is equal to minus of identity. So this operator, when extended C linearly on the complexified tangent space, we can see that it will have exactly two eigenvalues, square root of -1 and minus of square root of -1. And the this complexified tangent space can be then expressed as the disjoint union of these two eigenspaces. So then the square root -1 eigenspace is what is called as the holomorphic part, and the minus of square root -1 eigenspace is called as the anti-holomorphic part. So we take the holomorphic part of this TPMC and we call that as the TP10M. So this TP10M, and similarly we have TP0,1M. So TPMC, which is the complexified tangent space, that will be equal to the direct sum of TP10M and TP01M. So this TP10M, as we had seen in the last class, it is generated by the local frame del by del z del by del zi. So where every del by del zi will be equal to half of del by del xi minus square root -1 times del by del yi. So we take this del by del zi, which is equal to 1 by 2 times del by del xi minus root -1 times del by del yi. And then we take this collection of this as I varies from 1 to n. This will be generating the holomorphic tangent space. And similarly, if we take del by del zi bar, that will be 1 upon 2 times del by del xi plus square root of -1 times del by del yi. And then that will be the basis for the anti-holomorphic tangent space. So over here, and then the bundle of these holomorphic tangent spaces is the holomorphic tangent bundle. So over here, the holomorphic tangent bundle is a holomorphic vector bundle, whereas the complexified tangent bundle, that is a complex vector bundle. So this is the difference between a complex vector bundle and a holomorphic vector bundle. Okay, so let me go back. Okay, so I hope now these holomorphic tangent bundles and complexified tangent bundles are clear. Then the cotangent bundles are similar. So you take dzi instead of del by del zi. So dzi will be equal to dxi plus square root of -1 times dy, and then dzi bar will be equal to dxi minus square root of -1 times dy. So then these dzi generate the holomorphic cotangent bundle, and dzi bar generate the anti-holomorphic cotangent bundle. So we have these holomorphic tangent and cotangent bundles, and similarly we have the complexified tangent and cotangent bundles. Okay, so now the thing is that for these vector bundles, all the standard operations that are applicable to vector spaces, like direct sum and then tensor product and then dual, or like taking the dual, and all of these standard operations, they are exactly like they carry over to these vector bundles as well. So for example, the okay, just a minute. Okay, so for example, the dual of a holomorphic vector bundle will be so every fiber of that vector bundle is going to be isomorphic to CR. So we take like every fiber is going to be an r-dimensional vector space. So then we take the dual of all of those fibers, and in this way we get the dual of a holomorphic vector bundle. And so if capital V is the holomorphic vector bundle, its dual is sometimes denoted by V inverse or sometimes by V star or V dash. So this is the dual vector bundle. And then similarly, we can take the direct sum of two holomorphic vector bundles as well, V and W. So if we take the direct sum of each fiber point wise. So at every point P, there will be two vector spaces. One is V and one is W. We just take the direct sum, and that will give us another holomorphic vector bundle, which is called as the direct sum of these two vector bundles. Similarly, we have a tensor product as well, and then exterior powers, meaning the set of all alternating tensors, and also the symmetric power, meaning the set of all symmetric tensors. So these are so this is what is called as the exterior power k times of a holomorphic vector bundle V. Okay, and this exterior power is precisely what gives us higher dimensional forms. In like the higher dimensional differential forms are given by taking the kth exterior powers of the cotangent bundle. Okay. So then now that we have the holomorphic cotangent bundle, we can take the nth exterior power of the holomorphic cotangent bundle. So that is that capital lambda raised to n of the holomorphic cotangent bundle, and that is what we call as the canonical line bundle. So it will turn out be a rank one holomorphic vector bundle. So it will be a line bundle, and that line bundle is called as the canonical line bundle of a complex manifold. And then the dual of that canonical line bundle is called as the anticanonical line bundle. So this canonical line bundle is denoted by capital K subscript capital M, where capital M is the complex manifold, and then anticanonical is denoted by capital K subscript capital M, the whole inverse. So in this way, we have these canonical and anti-canonical line bundles as well. Okay, so now that we know about these holomorphic vector bundles and holomorphic line bundles, so we will now just see the notion of a Hermitian metric on a holomorphic vector bundle. So in the last class, we had seen the notion of a Hermitian metric on a complex manifold. So the Hermitian metric on a complex manifold gives a Hermitian metric on the holomorphic tangent bundle of that manifold. But the holomorphic tangent bundle is just one example of a holomorphic vector bundle. We can actually have the notion of a Hermitian metric on any arbitrary holomorphic vector bundle. So we have this notion of a Hermitian metric on any holomorphic vector bundle. Then we specialize to the case of the holomorphic tangent bundle. Okay, so what does this Hermitian metric mean? So on the holomorphic vector bundle, we know that every fiber is going to be a complex vector space of dimension r, where r is the rank of the bundle. So then we have on every fiber, we should be having a Hermitian inner product. So this should be a complex sesquilinear inner product. It should be linear in the first component and conjugate linear in the second component. So we have this Hermitian inner product on each fiber of the bundle, and then this assignment of every point to its to the Hermitian inner product on the fiber corresponding to that point. This assignment should be holomorphic. So this is like similar to the way we define a Riemannian metric on a smooth manifold. So it is a smoothly varying inner product on every tangent space of the manifold. So similarly, we have a holomorphically varying family of Hermitian inner products on each fiber of the bundle. So this is something which can be made of. Yes.
You really want your inner product to vary holomorphically or smoothly? Because
Like,
inner product cannot vary, Hermitian product cannot vary holomorphically. Because in the
so
second
the
coordinate, you have anti-holomorphic conjugation map, right?
yes. So the thing is, okay. So by the this thing, so like when we define the Hermitian metric on a smooth manifold, we actually define it to be a Riemannian metric. So that Riemannian metric is going to be the real part of the Hermitian inner product. So like over here, like I'm now taking this the Hermitian metric to be the complex to be the complex sesquilinear inner product. So that's why like I think in this case it makes sense to talk about varying it
I
holomorphically.
don't. Okay, so in that case, suppose you have a so what do you mean by smoothly or anyway varying, right? So you evaluate on vector fields, and then you get a map Cn valued or C
Correct,
valued.
correct,
Then you
correct,
take that map is holomorphic, right? In other words,
correct.
you are claiming that Z goes to norm of, let's say, gamma Z. Gamma is a section. Norm of gamma
Yes.
Z square is a holomorphic map, but it is not true.
Okay, okay. I see. I see. So then, so this should be like so this should be a smoothly varying family of Hermitian
Exactly.
inner
So
product.
here, Hermitian structure we want smoothly varied because we cannot
Okay,
have, like, it is a real analytic thing. So it's, if
okay.
you just write down the power series, you will get terms of Z and Z bar also, like in both both cases, right?
Correct, correct,
So it's a real analytic map. At the most, you can ask, you can demand it is a real analytic function on
correct,
a, when you evaluate on any vector field on your manifold.
correct. So I think in the book of Huybrechts, he had defined a Hermitian metric on a complex vector bundle, and over there he had indeed said that it is a smoothly varying family of Hermitian inner products. So I thought that
Yes, yes,
for a holomorphic vector bundle, it should be holomorphically varying. But yeah, I think you are right that even for a holomorphic vector bundle, it should be a smoothly varying family of
yes.
Hermitian
That is
inner
smooth
products.
always, actually. So I have also this confusion at some points, and one of
Yes,
my professor corrected me at some time.
yes, yeah. Thank you, Pralad. Okay, so yeah, so this is the correction. So over here, it should be smoothly varying instead of holomorphically varying. So we have this smoothly varying family of Hermitian inner products on each fiber of the bundle. So this is similar to the notion of a Riemannian metric on a smooth manifold. It is a smoothly varying family of real inner products on every tangent space of the smooth manifold. So we have this notion of a Hermitian metric on a holomorphic vector bundle, or as Prahlad said, we can also have it on a complex vector bundle. So we have the notion of a Hermitian metric on a holomorphic vector bundle as well as on a complex vector bundle. So okay, so then for these metrics, so just like in Riemannian geometry, we have these affine connections, and then so like the affine connection, maybe I can go to the whiteboard to write down. So let me just briefly recall the notion of an affine connection from Riemannian geometry, or the notion of an affine connection on a smooth manifold. So suppose now that this capital M is a smooth manifold, and this X of capital M is the set of all vector fields, the set of all smooth vector fields on the manifold capital M. So we have nabla to be a map from this X of M cross X of M going into X of M, where each X comma Y, capital X comma capital Y, where capital X and capital Y are any smooth vector fields on the manifold, it sends to the covariant derivative of Y with respect to X. So this nabla of Y with respect to X is called as the covariant derivative of the vector field Y with respect to the vector field X. So in this way, this connection enables us to differentiate vector fields. So we have this map. So this map should be bilinear in both the coordinates, and in the first coordinate it should be C infinity of M linear, where so this C infinity of M is what is called as the so this C infinity M is the ring of smooth functions on the manifold M, smooth real valued functions on the manifold M. So and then this X of M will be a module over C infinity of M. So first of all, this
So your
connection.
XM is global section of tangent bundle. Maybe I missed the notation. What is XM?
Yeah, XM
It is
correct. Yeah. So XM
global
is the
section.
set of all global sections of the real tangent bundle, which is same as the set of all smooth vector fields on the manifold.
Okay. Okay. Thanks.
Okay. So then this XM is going to be a real vector space, and it will also be a module over this ring C infinity of M. So we require this connection map to be bilinear in both the coordinates, are bilinear in both the coordinates, and then in the first coordinate it should be C infinity of M module homomorphism, and in the second coordinate it should satisfy the Leibniz rule. So this is what is called as an affine connection on a manifold, uh, and then or an affine connection on the tangent bundle of the manifold, because over here we are taking the set of all smooth vector fields, which are precisely the set of all global smooth sections of the tangent bundle of the manifold. So that's why. So this is what is called as an affine connection, and then in Riemannian geometry. So now if we equip this manifold capital M with a Riemannian metric G, then we get a Riemannian manifold, and then from Riemannian geometry we know that there exists a unique affine connection nabla on M, which is torsion free. So that means this nabla yx minus nabla xy is equal to the Lie bracket of x and y, and nabla respects the metric G, which is like saying the total covariant derivative of G with respect to nabla is equal to 0, or it is same as saying that the parallel transport induced by nabla is an orthogonal transformation in the inner product induced by G. So there exists a unique connection which is torsion free, and which respects the Riemannian metric G, or which is compatible with the Riemannian metric G, and this connection is called as the Levi-Civita connection. So in Riemannian geometry, we have got a canonical connection on every Riemannian manifold, or on the smooth or on the real tangent bundle of the manifold, which respects the Riemannian metric and which is torsion free, which is called as the Levi-Civita connection. So similarly, on a Hermitian holomorphic vector bundle, we have the notion of one more such canonical connection, which is called as the Chern connection. Okay, over here as well, if we are given a holomorphic vector bundle which is equipped with a Hermitian metric, then there will exist a unique torsion-free affine connection which will be compatible with the complex structure as well as with the Hermitian metric. So it being compatible with the complex structure means that if we take any global, if we take any local holomorphic section uh, of the vector bundle, then the nabla of that section is equal to nabla of that section with respect to those del by del zi bars, that should be equal to 0, and it respects the Hermitian metric as well. Such a connection is called as the Chern connection. So on any holomorphic vector bundle equipped with a Hermitian metric, we have a unique such canonical connection called as the Chern connection. And then this Chern connection naturally leads to the notion of curvature. So like now, given this Chern connection nabla, we can take nabla k and nabla l bar. So what are these? These are nothing but nabla subscript del by del zk and nabla subscript del by del zl bar. So these del by del zk and del by del zl bar, these will be uh, so these will be sections of the complexified tangent bundle, and then these are the covariant derivatives with respect to these sections. So this del by del zk will be a holomorphic vector field, and del by del zl bar will be an anti-holomorphic vector field. So then the thing is that these covariant derivatives in general do not commute, and the failure of these, the extent to which these covariant derivatives fail to commute is given by the curvature of the bundle. So if the covariant derivatives commute, then the curvature is 0. Otherwise, it is not 0. So this is what is roughly the curvature tensor. But we will see the formula for this curvature in the case of a smooth manifold. Okay. So before going to the
Just,
formula for the yes.
excuse me, I might forget. Don't you have this another term of the curvature, like nabla leaf bracket of the L and K, or that is that doesn't come here?
Yeah, like at least here it doesn't come. So the thing is that the precise formula for the Riemann curvature tensor of a complex manifold, I will be giving them in the coming slides. But like I was over here just giving the intuition behind this notion of a curvature coming from the connection. Like uh, given this connection, we have the notion of a covariant derivative, and then these covariant derivatives do not commute in general, and the
Right.
extent to which they fail to commute is measured by the curvature. So it is like something
Yeah,
similar to the notion of a
but
yes.
so is it really that, or this difference, the failure of being commuting curvature tensor, that versus these you are taking covariant derivative along the leaf bracket of these two vectors, right? So in general,
Uh,
Riemann curvature tensor, if I just go down to the hollow smooth category, then
yes.
it should be like lambda k, nabla l minus nabla l, nabla k minus nabla leaf bracket lk, right? So if I just l and k is just the vector bundles, the
Isn't that
vector
the
fields,
torsion?
right?
Isn't that the
Yeah, the
torsion?
torsion. Yeah, the torsion part.
Yes. Uh, okay. So like at least like in the
So yeah,
book of
that is what I don't know. Means in this particular form it might be like this,
yeah.
uh, but I'm a bit confused with how this formula matches with the usual formula for the curvature tensor. That is what my confusion is. Okay, you go on. We'll see then.
Yeah. Sure. Sure. Okay. So before going to this, the notion of a curvature, so we will. So we have now seen two notions of canonical connection, namely the Chern connection and the Levi-Civita connection. So for first of all, Hermitian metric on a complex manifold, as we saw in the last class, in the last talk, that it it provides again, sorry, again, smoothly varying family of Hermitian inner products on each holomorphic tangent space of the manifold. So a Hermitian metric on a complex manifold endows the holomorphic tangent bundle with a Hermitian metric. So then on the holomorphic tangent bundle T10M, there will exist this unique Chern connection. But now the Hermitian metric, as we had seen, is a Riemannian metric on the underlying smooth manifold, and this Riemannian metric is compatible with the almost complex structure, meaning we had seen that g of jx comma jy is equal to g of x comma y, where j is the almost complex structure. So this since this Hermitian metric G is also a Riemannian metric, so there will exist a unique Levi-Civita connection on the real tangent bundle, which is afforded by Riemannian geometry. And we had also seen that this real tangent bundle can be identified with the holomorphic tangent bundle in this way. So by using these identifications, the holomorphic tangent bundle, which will be spanned by these del by del z's, that can be identified with the real tangent bundle, which will be spanned by these del by del x's and del by del y. So the so yeah, so in this way the Tm is identified with T10M. So now that Tm and T10M are identified on T10M, we have this canonical connection, which is the Chern connection, and on Tm we have the usual Levi-Civita connection, which is given by Riemannian geometry. So then the question that arises is when do these canonical connections coincide with each other? And the answer to this question is that, so like this is a theorem from Kähler geometry, which says that the Chern connection and the Levi-Civita connection, they will coincide if and only if this Hermitian metric satisfies the Kähler condition, which we had seen in the last class. So that's why this Kähler, the notion of a Kähler metric is important, because because this is true only for Kähler metrics, that the Chern and the Levi-Civita connections coincide. So I will now once again go to the like the definition of Hermitian and Kähler metrics. Okay, so I hope everybody can see the screen, this screen as well. So yeah, so this Hermitian metric was nothing but a Riemannian metric on the manifold, which respects the almost complex structure on the manifold. So this almost complex structure J, it should be an orthogonal transformation in the inner product, which is induced by the Hermitian metric, by the Riemannian metric. Then that Riemannian metric is called as a Hermitian metric. And then for the Kähler condition, we take this real 2 form, which is defined in this way: omega of x comma y is equal to g of jx comma y. So this will be an alternating like antisymmetric bilinear form, and then this omega if it is closed, that is d omega is equal to 0, where d is the exterior differential, then then G is said to be a Kähler metric, and omega is said to be the Kähler form associated with G. But then this Kähler metric and its associated Kähler form, these are in one-to-one correspondence with each other, and that's why we also sometimes say that omega is a Kähler metric on them. And then as we saw that the Chern and the Levi-Civita connections correspond if and only if the Hermitian metric is scalar. So that's why the notion of a Kähler metric is very important. And one more thing that we had just discussed in the last class is that a Kähler metric is a Kähler manifold is a manifold on which there are three structures which are compatible with each other. One is the complex structure, the other is the Riemannian structure, and the third one is the symplectic structure. So this omega is going to be a symplectic form. So yes, so a Kähler manifold is precisely a smooth manifold on which all of these three structures are compatible with each other. Okay, I will now be giving the formulas of these Riemann curvature tensor and then the Ricci curvature form as well as the scalar curvature. So first we'll just see some of these notions which are some terms which are used in Kähler geometry. So a Kähler metric on a complex manifold capital M gives a Kähler manifold, and then as we saw, this omega is going to be a closed 1,1 form. So 1,1 means that it is a two form in which so it's like these dz's give 1,0 forms and dzi bar give 0,1 form, and then if you have something like dzi wedge dzj bar, that is a 1,1 form. So okay,
Yeah, Rajas, are you there?
yes, yeah, I'm there.
Oh,
Okay, so this omega being a closed 1,1 form, it will define a cohomology class. So this H11MR is the set of all Dirac cohomology classes of smooth 1,1 forms. So then the cohomology class of this Kähler form omega is called as the Kähler class of omega. And then if you have any general cohomology class coming from this real cohomology space, Dirac cohomology space H11 of M comma R, then if there exists a Kähler metric which represents this Kähler class, then this Kähler class which represents this cohomology class, then this cohomology class is called as a Kähler class. And then the set of all Kähler classes like cohomology classes which are represented by Kähler metrics in this H11MR is denoted by H11MR plus and is called as the Kähler cone. So this is a cone, meaning it is closed under addition and it is closed under multiplication by positive real numbers. So these are some notions that are there in Kähler geometry. Then one more property about these Kähler manifolds is that so we will be mostly dealing with compact Kähler manifolds. So if we have a compact Kähler manifold, then suppose we are given two closed so these zeta sorry, xi and eta, these are smooth 1,1 forms which belong to the same Dirac cohomology class. So they are closed smooth 1,1 forms which belong to the same Dirac cohomology class, which means that the difference xi minus eta is going to be d of something. It is going to be d exact. But then this del bar lemma says that the difference xi minus eta is also going to be del bar exact. So there will exist a smooth function f such that xi minus eta will be equal to square root of -1 times del bar of f. So what this lemma is trying to say is that in the case of smooth manifolds, we have the de Rham cohomology, and for these complex manifolds, we also have something called as the Bott-Chern cohomology. So this del bar lemma is saying that so in the Bott-Chern cohomology, the exterior differential is going to be this square root of -1 del bar. So this del bar lemma is trying to say that for Kähler manifolds, the de Rham cohomology is isomorphic to the Bott-Chern cohomology. But we don't need to go into the details of this. So this is just one property which Kähler manifolds satisfy. Yeah. So like now these are the expressions for the Riemann curvature, Riemann and Ricci as well, curvature tensors, which are given in terms of local holomorphic coordinates on the manifold. So now this M will be an n-dimensional complex manifold. It need not be compact. So, okay. And then this G is given to be a Kähler metric on M with associated Kähler form omega. Then we just take some local holomorphic coordinates Z1 up to Zn. So over here, the reason why I'm writing these indices 1 up to n as superscripts is that so that like these will enable us to use that tensor notation or the Einstein summation convention as well. So that's why we are writing the indices as superscripts. So Z1 up to Zn are local holomorphic coordinates, and then we will be having the vector fields, holomorphic vector fields and anti-holomorphic vector fields, which are del by del Zi and del by del Zj bar. So we simply take G of this pair and we call it Gij bar. So then it will turn out that this Gij bar, G subscript I comma J bar. So this will be a positive definite Hermitian matrix. Uh, and this is what is called as the Hermitian matrix of the Kähler metric. So this Gij bar is a positive definite Hermitian matrix. So we take the matrix inverse, and the tensor notation for the inverse is this G superscript I comma J bar, and then the Riemann curvature tensor is a 4 tensor. That is R subscript I J bar K L bar, and that is defined by this formula. So this is what is known as the Riemann curvature tensor, but this is a bit difficult to work with and also a bit difficult to compute. So we have a simpler notion of curvature tensor, which is called as the Ricci curvature tensor. So we just take the metric contraction of this Riemann curvature tensor with respect to the metric G. So this R I J bar, so this will be a 1, 1 tensor. So this R I J bar, which is the Ricci curvature tensor, is given by this expression. And then the trace of the Ricci curvature tensor is called as the scalar curvature, which is given by this way. So this capital R will be a smooth function on the manifold. So okay, so these are the expressions for the respective curvature tensors. Fine. So like after doing this, I will just go start defining the Ricci curvature form and then the Chern forms and Chern classes, because these are the things which are required in the definition of Kähler-Einstein CSCK and extremal Kähler metrics, which are the main objects of study in this series of talks. I hope that the screen is now visible. Okay, so we will now see the notion of a Ricci curvature form or the Ricci form. So we are now on a compact Kähler n manifold capital M, and we have a Kähler metric, a fixed Kähler form omega, and then as we saw with this omega, we can associate a Hermitian matrix, which is called as the Hermitian matrix of omega, and that was that Gij bar. So this H of omega is going to be the Hermitian matrix of this omega given in terms of some local holomorphic coordinates. And then we can take the determinant of omega, which is the determinant of H of omega. This determinant of omega will turn out to be independent of the coordinates, even though the Hermitian matrix actually depends on the coordinates. So then the Ricci curvature form, Ricci of omega, is defined by this formula. It is minus square root of minus 1 del bar of the natural logarithm of the determinant of omega. So this determinant of omega and hence its natural logarithm are going to be smooth real valued function on the manifold capital M. So this is nothing but minus root minus 1 del bar of a smooth function. So that's why this will be a closed 1, 1 form. So
So
okay,
that means
yes,
Ricci form. That means Ricci form is just the curvature of the canonical bundle, right?
correct. Curvature of the anti-canonical bundle.
Oh, and okay, that I'm not able to see why. And what is anti-canonical? The determinant bundle is the canonical bundle or anti?
Sorry, what did you say?
Determinant bundle of the tangent bundle is the canonical bundle or anti-canonical bundle?
It's the anti-canonical bundle.
Okay. And what is then canonical bundle? I don't know those things. That's why I'm
Yeah, so
asking.
the canonical bundle was that, so you had that holomorphic tangent bundle, and then you take
Yes.
the nth exterior power of the holomorphic tangent bundle. That will be the
Yes.
canonical bundle.
And what is anti-canonical bundle then?
That's the dual of the canonical bundle, and that will actually turn out to be equal to the determinant bundle.
Uh, uh, Okay, in mine, in my mind, I thought so if the dimension of the manifold is n, then nth exterior product of the tangent bundle is the essentially the determinant bundle. So is
Yeah,
it's not
yeah,
the
they will
case?
be. Yeah, sorry, what did you say? The determinant bundle is what?
Suppose I have a manifold of with complex manifold or Kähler manifold, whatever manifold of dimension n, let's say,
Correct.
right? Then
Yes,
if I take the tangent bundle, that is a bundle of rank n,
correct.
right? And then if
Yes,
I take the nth exterior product of that bundle,
correct.
then I see. So I need to get the determinant bundle, I should take nth exterior product of the cotangent bundle. That is
Correct,
why
correct, correct,
I understand. Yeah,
correct.
yeah. Thank you. Sorry for interrupting. Sorry.
Yeah, yeah. Yes. So exactly as you pointed out, this Ricci curvature form is it's the curvature form of the anti-canonical line bundle. So associated to every compact Kähler manifold or even non-compact will also do. So there will exist this anti-canonical line bundle, and then these curvatures of that manifold are precisely the curvatures, the corresponding curvatures of the anti-canonical line bundle. Okay, so this uh, Ricci of omega, because it is square root minus 1 del bar exact, and as we saw by the del bar lemma, that de Rham cohomology and the Botchan cohomology are precisely going to be isomorphic for Kähler manifolds. So that's why this Ricci of omega is also going to be declosed. So this is a declosed 1, 1 form on M, and then we can have its real cohomology class, the de Rham cohomology class. So it can be checked that if we take two different Kähler metrics, omega and eta on M, then Ricci of omega is this. Ricci of eta is similarly over here, it will be determinant of eta. And then if you take Ricci of omega minus Ricci of eta, it will be it will be some square root minus 1 del bar of a smooth function. So it will be exact. So that's why the difference between Ricci of omega and Ricci of eta is going to be exact. So that means they belong to the same cohomology class. So given any smooth, given any Kähler metric on the compact complex manifold M, the Ricci forms always land up in the same cohomology class, and then the 1 upon 2 pi of this cohomology class is called as the first Chern class of the manifold. So this first Chern class of the manifold is going to be independent of the choice of the Kähler metric on the manifold. And then 1 upon 2 pi of the Ricci curvature form is called as the first Chern form. So the first Chern form is nothing but a scalar multiplied to the Ricci curvature form. And and this is the first Chern class. So these are the notions of Ricci curvature form, first Chern form, and first Chern class of a compact Kähler manifold. And then using these, we can define what are Kähler-Einstein and constant scalar curvature Kähler metrics. So a Kähler metric omega is said to be a Kähler-Einstein metric if, as the name suggests, it is a Kähler metric which satisfies the Einstein condition, meaning the Ricci tensor is going to be proportional to the metric tensor, or the Ricci curvature form should be proportional to the Kähler form. So there exists some constant lambda belonging to real numbers such that Ricci of omega is equal to lambda times omega. Then it is said to be a Kähler-Einstein metric. And this lambda is called as the Ricci curvature of this Kähler-Einstein metric. Okay, so and then we can so this scalar curvature of a Kähler metric, it can be quickly computed by this formula as well. Namely, if we take the Ricci curvature form and wedge it with omega raised to the power n minus 1. So there is one more fact about these Kähler manifolds is that the Kähler form omega which we had, the Kähler form omega, if you take that omega raised to the power n divided by n factorial, that will precisely give you the volume element on the manifold. So this omega raised to the power n divided by n factorial is the volume form. So that's why, so this is like Ricci of omega wedge product with omega raised to the power n minus 1 divided by n minus 1 factorial is equal to S of omega times omega raised to the power n divided by n factorial. If you divide this whole expression by n factorial, so this is like, so we have two top dimensional forms on both the sides, and then there always has to exist a unique smooth function such that this equals this, and that smooth function is precisely what we call as the scalar curvature of the metric. So this S of omega is the unique smooth real valued function on capital M which satisfies this expression. Okay, so now that we have this S of omega, we can define a constant scalar curvature Kähler metric, which is also abbreviated as CSCK metric in Kähler geometry. So a CSCK metric is simply a metric, a Kähler metric where this S of omega is a constant function. So that is what is called as a CSCK metric, and we can then easily see that if this metric is Kähler-Einstein, we can simply wedge this equation with omega raised to the power n minus 1 on both the sides. That will give us that omega is CSCK as well. So Kähler-Einstein implies CSCK. Okay, and then both these Kähler-Einstein and CSCK metrics, they are special cases of a larger class of Kähler metrics, which are called as extremal Kähler metrics. So this the notion of an extremal Kähler metric was introduced by Eugenio Calabi. We first define what is the Calabi functional. We are fixing a Kähler class on the manifold M, and then we are taking the set of all Kähler forms belonging to the Kähler class. Then we define this capital Cal from omega plus 2r in this way. So this is the norm square of the L2 norm square of the scalar curvature of the metric omega. So this is the Calabi functional. And then Calabi suggested looking at the critical points of this functional belonging to the fixed Kähler class. And then the critical points of this functional are called as extremal Kähler metrics. Okay, the critical points of the Calabi functional are called as extremal Kähler metrics. So then Calabi also gave an Euler-Lagrange equation which characterizes these extremal Kähler metrics. So okay, so I can maybe write down that this what it means to say that omega is a critical point on the whiteboard. I will write down. So okay. So this is how the variation in a fixed scalar class is given by. So like we saw by the del bar lemma that any two scalar forms which belong to the same Dirham cohomology class, they have to be like the difference has to be equal to square root of minus one del bar of some smooth function f, globally defined smooth function f. So then we can take omega t to be equal to omega plus t times square root of minus 1 del bar of f, where t varies over the closed interval 0 comma 1. So then omega 0 will be omega and omega 1 will be this omega plus square root minus 1 del bar of f. So this is what is called as the variation of a Kähler form in a fixed Kähler class. And then what we do is that we take we take this Calabi functional, we compute it at omega t. Sorry. So we compute the Calabi functional at omega t, and then what we do is that we take the derivative of this with respect to t at t equal to 0. And if this derivative equals 0, then omega is said to be a critical point of the Calabi function, which is then by Calabi's definition, it is called as an extremal Kähler metric. So this is what it means by metric omega is a critical point of the Calabi function. Okay, so then these extremal Kähler metrics also have got like that d by dt of the Calabi function of omega t has to be equal to 0. That gives us a Euler-Lagrange equation which characterizes them, and that Euler-Lagrange equation is precisely this: that if we take the 1 comma 0 gradient of the scalar curvature, which is nabla 1 comma 0 of s of omega, and this is precisely equal to del bar of s of omega, the whole sharp. So this so we know that in Riemannian geometry associated to every Riemannian metric G, we have these musical isomorphisms which are sharp and flat. So these musical isomorphisms are going to be isomorphisms of the tangent bundle and the cotangent bundle in Riemannian geometry. So similarly, because the Hermitian metric has got an underlying Riemannian metric, so that's why we have these musical isomorphisms, sharp and flat as well. So this del bar of s of omega, so this will be a 0 comma 1 form, and then when we take its sharp, it will give us the 1 comma 0 vector field which corresponds to this thing under this sharp isomorphism. So then this nabla 1 comma 0 of s of omega, which is a 1 comma 0 vector field, if it is a holomorphic vector field, meaning del. Yes.
Just I want to interrupt here,
Yeah.
like as I don't like this sharp and this thing because I
Yeah.
always forget. But it is nothing but the isomorphism induced between a vector space and its dual. If the vector space is equipped with an inner
Correct.
product,
Correct.
right?
Yes. Yes. Correct. Correct. Yeah.
So
Exactly.
there is
Yes.
a thing. So essentially here 1 0 goes to 0 1 or so on and so forth because you have Hermitian product, right? So one is
Correct. Correct.
isomorphism or another one is anti-isomorphism.
Yes, yes.
Yeah. Okay. Yeah. Thank you.
Yeah, okay. So this nabla 1 comma 0 of S of omega will be then 1 comma 0 vector field on the manifold M. And if this 1 comma 0 vector field is a holomorphic vector field, meaning del bar acted on this 1 comma 0 vector field is equal to 0, then the metric omega is an extremal Kähler matrix. So this is an equivalent characterization for extremal Kähler matrix. And then over here, this real holomorphic vector field simply means that like we saw that the real tangent bundle can be canonically identified with the holomorphic tangent bundle by those identifications that del by del zi maps to half of del by del xi, and then square root of minus 1 times del by del zi maps to half of del by del yi. In that way, the T10M and TM, they can be canonically identified with each other. So if we take a real vector field, we look at its corresponding holomorphic vector. We look at its corresponding 1 comma 0 vector field, and if that corresponding 1 comma 0 vector field is a holomorphic vector field, meaning del bar of that is 0, then this real vector field is called as a real holomorphic vector field. So okay, so this is what it is. And so this is the equivalent characterization for extremal Kähler matrix, and this is precisely the condition which is actually used for checking whether a Kähler matrix is extremal or not. And then we can check that CSCK will imply extremal Kähler, because for if omega is a CSCK metric, then this S of omega will be a constant, and that's why this will be equal to 0, and hence it's a holomorphic vector field. So that's why CSCK will imply extremal Kähler. So extremal Kähler matrix contain these CSCK as well as Kähler-Einstein matrix as special cases. So these three are the most well-known and well-studied notions of canonical Kähler matrix. So these canonical Kähler matrix, as I will go on the last page. So these canonical Kähler matrix are some Kähler matrix which satisfy some nice curvature related properties. So these Kähler-Einstein, CSCK, and extremal Kähler matrix are the three most important notions of canonical Kähler matrix in Kähler geometry. And as we saw over here, in the definitions of these metrics, the scalar curvature is involved, and the scalar curvature is directly related to the Ricci curvature form. And then the Ricci curvature form directly gives the notions of this first Chern form and first Chern class. So then we take the analogies of these things to the level of the top Chern form and the top Chern class, and then we get to what are called as these higher CSCK and higher extremal Kähler matrix. So for that, first let us just see how we define the higher Chern forms and the higher Chern classes. So we take this expression, determinant of I plus A, where I and A are any I is the n cross n identity matrix, and A is any n by n matrix. And then this, if we expand the entries of this, so this will be like we compute the determinant in terms of the entries of these matrices. So this will be equal to this thing, where P1 will be equal to the trace of the matrix A, and Pn will be equal to the determinant of the matrix A, and then P2 will be the sum of all the eigenvalues of A taken two at a time, the sum of products of eigenvalues of A taken two at a time, and so on. So in this way, we have these invariant homogeneous polynomials Pk in the entries of the matrix A. So now we want to define the kth Chern form of omega. So we take the Kähler form omega on M, and we take the Hermitian matrix of it. Then this theta of omega, which is defined by this formula, del bar applied to H inverse del H of omega. So this is called as the curvature form matrix of omega. So this will be an n cross n matrix whose entries will be closed 1 comma 1 forms. So this is the curvature form matrix theta of omega. And now if we take suppose we want to see the first Chern form, so then the first Chern form will be this P1, which is the trace. So the first Chern form C1 of omega will be the trace of the curvature form matrix. So it will be 1 by 2 times trace of square root of minus 1 times theta of omega. And then this definition will precisely match with this definition as well. So So this is the first Chern form. Similarly, we can compute the higher Chern forms as well. So the kth Chern form Ck of omega is defined as Pk, where Pk is the kth invariant homogeneous polynomial. So it is Pk of square root of -1 upon 2 pi times theta of omega. And then this Ck will be a closed Kk form, just like the Ricci curvature form was a closed 1-1 form. So this is a closed Kk form. And then once again, it can be checked that if we have two different Kähler metrics, omega and eta on the manifold M, then Ck of omega and Ck of eta, they will land up in the same de Rham cohomology class. So the de Rham cohomology class of Ck of omega is called as the kth Chern class of M, which is independent of the choice of omega. And okay, and so we are basically going to be interested in the top Chern form and the top Chern class. So the top Chern form Cn of omega is defined as the determinant of square root of -1 upon 2 pi times theta of omega, because Pn is the determinant. So like the first Chern form or the Ricci curvature form was the trace of the curvature form matrix, whereas the top Chern form is the determinant of the curvature form matrix. So Cn of omega is called as the top Chern form, and we have Cn of M, which is the top Chern class. So now from this Cn of omega, we get another notion of curvature, which we dub as higher scalar curvature by analogy. So what we do is that Cn of omega is going to be a closed n comma n form. N comma n, so it will be a real 2n form, which will mean that so since the manifold has dimension 2n over the reals, so that's why this will be a top dimensional form. So Cn of omega is a top dimensional form, and omega raised to the power n divided by n factorial is the volume form. So there will exist a unique smooth real valued function lambda, which will satisfy this expression, globally defined smooth function, which satisfies this expression, that Cn of omega is equal to lambda divided by n factorial into 2 pi to the power n times omega to the power n. So this 2 pi to the power n is just meant for balancing with this. So if we take determinant over here, 1 upon 2 pi raised to the power n will come out. So that's why just to balance that, we are having that over here as well. So this lambda is what can be called as the higher scalar curvature of omega. And then the metric omega is said to be a higher constant scalar curvature Kähler, or higher CSCK, if this higher scalar curvature, which is also a smooth function, if it is a constant function, we call the metric as a higher CSCK metric. And then similar to this Euler-Lagrange characterization for the extremal Kähler metrics, where we have this thing nabla 1, 0 of the scalar curvature, we instead take nabla 1, 0 like the 1, 0 gradient of the higher scalar curvature. If this is a holomorphic vector field, then the metric is said to be higher extremal Kähler metric. And then once again, we can check that if omega is higher CSCK, this lambda will be constant, and that's why this vector field will be 0, so it will be holomorphic. So if omega is higher CSCK, then omega is higher extremal Kähler. So in this way, Professor Pingali introduced these notions of higher CSCK and higher extremal Kähler metrics, which are a top dimensional generalization of these notions of CSCK and extremal Kähler metric. Okay, so now we have two additional notions of canonical Kähler metrics, which are higher CSCK and higher extremal Kähler metrics. Okay, so yeah, I think I should stop over here, and these are the reference books which you can see. So this extremal Kähler introduction to extremal Kähler metrics by Gabor Sekehiri. This is the book which deals with the theory of these extremal Kähler metrics, and also Kähler-Einstein metrics. Most importantly, the recent advances in the theory of Kähler-Einstein metrics. All of those things are discussed in this introduction to extremal Kähler metrics. And for studying about the some basics of complex geometry, one can refer to this complex geometry book by Huybrechts. Okay, yeah, fine, thank you.
Okay, so thank you.
So I have a
Any
question.
question? Yeah.
So
Yes.
so you are defining Chern classes Cn for canonical bundle. Similarly,
Yes.
for other vector bundle or particularly line bundle also, it can be defined, right?
Correct. Yes,
Yeah,
definitely. And then the
in particular, that you have defined everything for canonical. For if you take anti-canonical, then I mean this calculation, it should be that minus of that number you are getting for canonical.
the thing is that the Kate-Chan form
No,
of
no. I am it is line boundary, so we can only find the C1 for.
yeah
Yeah, so that should be. I mean, I guess I didn't. I mean, check the formula properly. So, if I take anti-canonical, then
yeah
C1 of anti-canonical would be that. I guess similarly, if I define the Ricci of anti-canonical,
yes.
and then maybe C1 of anti-canonical would be minus of this number. Is it?
Uh, no, the thing is that c- the Ricci form of the metric omega on M. So like this omega will induce a Hermitian metric on the anti-canonical line bundle, and then the curvature of the metric on the manifold is equal to the curvature of the induced metric on the anti-canonical line bundle. So it will be minus of that of the canonical bundle.
Yes, that's what I'm telling. So your
Yes,
omega is
yes.
canonical, right?
Sorry,
Your this omega, small omega is canonical, right?
what does it mean by a
No,
canonical?
no,
Like
no. I mean,
omega is a Kähler form.
okay, Kähler. Okay. This one is Kähler form, and then you are defining C1 of this. Okay. So
Yeah.
and then what I am asking that uh, no. Uh, I mean, no, I thought that small omega is that the okay, be the Kähler matrix. Okay, I may confused with that the line bundle canonical or with this omega. Okay.
Okay. Yeah. Omega
Yeah,
is the Kähler form
actually,
associated to the Kähler metric.
Okay.
yeah, Navanita.
Yes. Yes.
Yeah, actually, see here, omega is the Kähler form associated with the Kähler metric. So essentially, you have this metric of the tangent bundle of that Kähler manifold M.
Hmm.
Now,
Yes.
if you go to the so once you have so now you take the cotangent bundle of M, and
Yeah.
then you go to the canonical bundle after taking diamond
Yes.
n many wedge product. So
Hmm.
Yes.
essentially the
Correct.
determinant bundle. So
Yes.
in that determinant bundle, the metric becomes determinant of omega, right? Because
Hmm.
omega is the
Hmm.
Yes.
metric of the given n-dimensional bundle. So then this Ricci omega actually becomes the curvature of that line bundle. So anti-canonical bundle to the compact manifold M. So that is how this C1W is essentially this Chern form or Chern connection, Chern class is kind of an anti-canonical one correspond associated to this manifold M. That is what I kind of pointed out there.
Yeah.
Okay. Okay. Thank you.
Yeah.
Okay. So any other question? Okay, then maybe we can virtually thanks Rajas, and he will continue on like next Wednesday for his final talk. Okay, so thank you, Rajas.
Yeah.
Thank you,
Thank you,
Rajesh.
Sachidanand.
And I'm
Yeah.
sorry I interrupted so much for today.
No. You like I like questions like this should be asked in between the talks so that like it becomes more interactive for the other participants as well. So yeah. So like that was a good thing. That was like
Thank you. Thank you so
yeah.
much.
Yeah. Thank you. Yeah. Thank you.
Okay.